Thank you, Mr. Chairman, and this kind introduction. And thank you also for coming to my talk, my second talk. I just wanted to show you now where Montpellier is. This is France. So Montpellier is just on the south of France, and you have a medical institute here, Italy, and Spain. So this is one of the, this is the greatest. This is the old pedestrian place in Montpellier. So if you have the opportunity to visit us, please come and see us. Okay, on Monday I was talking about hybrid silica, the nanostructuring of these silica, and now I'm going to show you some of the application of these materials. So this is just a reminder of what I was saying about solid chemistry. Silica can be formed from tears by condensation and hydrolysis. You can have many forms of these materials. I will talk today about mainly nanoparticles, about some film, and also about powders for this. And this also is again what I told on Monday, just to remind you. But we could self-structure these materials by using molecular interaction of these organics, bridging organics. But you can also use surfactant external structuring agents to get mesoporous materials. And today I'm going to talk about how we can use both the silica matrix and the bridge organosilane from where we are going to use, for example, ligands, or for example, from these ligands we can make ion uptake, or we can also use for catalysis, and we can also have optical properties. And from this we are going to mix also the mesoporous materials to get some medical applications. Okay, let's talk about, just come back. So structuring was there, and also structuring here, but we can also obtain amorphous compound from this solid chemistry, starting from these precursors. And these amorphous, which is dioxane, of course, has got also the bridging unit, and from this I'm going to talk about a little bit, just briefly, about catalysis, catalytic applications, and also from photoluminescence application. I will just give you one example of which dioxane, which can be used as catalyst and also as films for luminescent materials. Okay, I will then talk about nanomedical applications. So this is the bridge dioxane of which I'm going to talk with the bridging bipyridine moiety, and you can prepare this from bipyridine, of course, and then just make oxidation, nitration, reduction, and then silylation, and you get, after hydrolysis condensation, you can get your materials here, which I can use as powder for catalysis reaction, and we can use also as films for luminescent materials. So catalytic application. You have here in our lab, there's an organic chemist who used to do this sort of cross-coupling reactions using alcohol with halides, aromatics. And normally you use palladium or platinum catalysts, which are very expensive and very toxic also. And he, in our lab, he used copper, which is much less expensive, much cheaper, but also less toxic than palladium and platinum. And at the time he was doing this, it's called the Ullmann type reaction, he used 15% of copper, which is not good for catalytic reactions. And then he could reduce until 20%. But then the reaction doesn't work as well as what he was using for 50%. What we decided to do is to immobilize this catalyst just by doing what I showed you before, the sol-gel reaction, to get this powder, and where the bipyridine is immobilized in the solid. And from this we are going to complex the copper, and then we do the reaction. And in this case, I have put here 10%. In fact, we can now reduce to 2% and it works. Okay? And you can see here the reaction from this bromobenzene with this phenol works perfectly well, and this is 90% isolated yield. Okay? And the main thing is that when you finish the reaction, you just filter, because your catalyst is completely insoluble. You filter, you recover the catalyst, and you can wash and use it again. And use it again to do the same reaction. And what we did is to change, instead of using bromobenzene, you can use now methoxybromobenzene with the same catalyst, and you can recycle to do this same type of reaction with now different substituent, still the same conversion. And you can continue this with cyano groups, with also pyrimidinol groups, nitro groups here, again aromatic, and also with withdrawal group. And you can continue this, just filter. And we did it, my student did it 10 times until she stops, because she had to finish her PhD. Okay, so this works, and I just want to show you this was the Bush-Cistioxane, and we are going to use the same compound, same materials here to get films instead of using powder. And from these films, we were lucky enough to see that they are photoluminescent, and just by using this kind of commercially available lanthanide gallium nitride system, LED, and you can enhance these photoluminescence and get blue emission from this. Okay? Right, so I finished with the amorphous materials. I'm now coming to the mesoporous materials, and I'm going to show you how we can use these nanoparticles, mesoporous nanoparticles, to put drugs inside and to deliver the drug with control, which we can control for the delivery. Okay? So I will give you two kinds of examples, one which is pH sensitive and the other one which is bioresponsive. Okay, so why are we interested with these sort of mesoporous nanoparticles? We know that silica can be prepared mesoporous, like we saw in many talks since Monday. And from this, we know also that you can increase and also have selective introduction of these nanoparticles into cells. Okay, they are quite comfortably done. And also what is interesting is that when you put the drug, you protect the drug inside these nanoparticles. And so you may just reduce, for example, side effects, okay, when it is protected inside. And then also you can, of course, put some hydrophobic drug transportation, which won't be easy in the bloodstream. Okay, the other thing is that these nanoparticles have got many pores, and you can put many drugs inside. You can load the drug with a high loading capacity, and they are known to be of low toxicity. We are checking this now, and what we want to do next is try to just put the drug inside, cap it, block it, and then just release on demand these drugs. Okay? So this is the next thing I'll tell you about a little bit of biology. This represents the bloodstream here, and you have here three kinds of cells, where the healthy cells are in yellow here, and the brown are the tumor cells. Okay? And you have a third kind of cells, which are here, like a membrane, which we call the endothelial cells. When you are just having healthy cells, these endothelial cells are well arranged with very well homogeneously distributed intervals, space in between these cells. But if you have the tumor cells, then this will create defects, and you will enlarge these windows like this. And what we want to do is to get our nanoparticles, which are these small balls here, inside this selectively. And this is how we want to do it, using these windows. If we are able to prepare these nanoparticles which are big enough to not enter this space, and which are small enough to get into this space, then you are targeting the tumor cells. Okay? The other thing is that we know that in the cells, the pH is acidic, whereas in the bloodstream pH is neutral, about 7 to 7.5, 7.4 pH. Okay? And what is interesting is that if you can travel, you can get your drug traveling inside the bloodstream, block into the nanoparticle, and then get the nanoparticle inside the tumor cells. As soon as it gets into the tumor cells, it will reach acidic pH. And if you have something which is pH responsive, then you can unlock your nanoparticles and deliver directly your drug inside these cells. Okay? And this would help in reducing side effects. Okay, so to do nanoparticles, we have many sort of this. So I talked about mesoporous silica, which is here. So mesoporous silica can be done directly, but you can also functionalize them just by doing some grafting or by doing some topical surgery, like I was saying 2 days ago. And then you can afterward put drugs inside and block. Okay? Same thing which you can do, I was saying about closer gel. So starting from tears, sorry for this, there's a problem with my drawing. This is a bridging unit, which is here. And you can do some, let's say, mesoporous organosilica nanoparticles here, where you have these bridging units in the wall here. Okay? You can also prepare, I'm really sorry for this, you can prepare directly peerables without tears and obtain a pure pearly mesoporous silica. And you can mix also 2 bridge organosilins to get a mixed peerables. And finally, you can also do nanoparticles without any pores. And I will give you one example where you use only the bridge organosilin to obtain some dense nanoparticles. And this can also be used for cancer treatment. Okay. This is our aim, is to functionalize, this represents the one mesopore, where you can put a drug, and then on one functionalization you can cap with a big molecule, for example, and what we want to do is to deliver, to open this cap just by direct excitation, like of what I call here a mechanized hybrid silica. Okay? We can also do this just by using some, let's say, a signal which we can have here on the wall, which we can transfer again to this cap and deliver again. And we can also graft 2 stopes here, and one which is going to transfer its energy to this cap. I'm going to give you one example of each of these. Okay, so let's start from this. I will talk about pH sensitivity system. So this represents one mesopore, and the concept is the way you are going to graft your stock here, which is acetylioxane, for example, and then you are going to put cargo molecules, for example, the drugs or chromophones. I will give you the examples, and then we are going to cap this with this sort of big molecules like cyclohexane. Okay, and at pH acidic, then you can just cleave this interaction between the red semi-balls and the stalk, and just deliver the drugs. Okay, here on Monday I showed you how we could prepare this rich acetylioxane with a melamine system, and I showed you that we can use it to do molecular imprinting with cyanuric acid. Cyanuric acid has got 3 phases with a donor-acceptor-donor system, which can be with interaction between, I said donor-acceptor, donor-acceptor, and which will interact with the donor-acceptor-donor of hydrogen here of the melamine. And in this case, we use uracil, and which was grafted the cyclodextrin. This is already described in literature, the synthesis of this. Okay? So I will just skip the synthesis. And the idea is to graft this, or what we call MCM41, for example, which was done with TIOS and CETA, cetyl trimethyl ammonium bromide, to get this MCM41 plus precursor. If you look at this, then this can be proved by infrared. I'm sorry, you can't find it in blue here. You have the precursor, the footprint IR of the precursor, and what unfortunately you cannot see in the red correspond to, in green, correspond to the MCM, so this is flat completely. So believe me, this is completely flat. Okay? And finally, when you graph it, you can see the footprint of this moiety here in the red, which is doing the same thing like in blue. The other thing to prove this is by silicon NMR. So this is Q units representing MCM41, and when you graph this is cis-diopsanes, so you have a lower field chemical shift of this system. And finally, to prove this, we have 10 pictures to prove that these are really nanoparticles of about 50 to 100 nanometer size. And unfortunately, you can't find it, but we are most close. Okay, we are now going to load and how can we proceed for the capping. So to load this, we have chosen 3 kinds of carbon molecules. There's 2 chromophores, propidium iodide, rhodamine, and camptothecene. Camptothecene is just a drug, and these 2 are going to just prove how we can cap and uncap the molecules outside and inside the cells. Okay? So propidium iodide, we just did it without cells, and this is just to show you that when we don't put acid, this is neutral condition. There's no release of the propidium iodide, so there's no fluorescence. And then as soon as you add pH 6, for example, which is here, 6, 5, 4, 3, you can see that there's a fluorescence emission, and so showing that the propidium iodide is going out, so it's completely uncapped. So this is hydrogen bonding cleavage by HCl. Okay? The second thing we did is to show that the nanoparticles goes inside the cells, which are non-healthy cells, and then what we can release them, and afterwards we can put drugs also, just to confirm that we have some cytotoxicity of this due to these nanoparticles. So this is the second thing we did. We put rhodamine D, which is the second chromophore, and we capped again, and then we just treat them, put them in suspension with some cells, tumor cells, which is breast cancer cells here. And this is just a control. There's no nanoparticles without chromophore. Okay, so there's nothing which you can see. And then when you put chromophore, you can see that these are the red dots due to the nanoparticles which has been introduced inside, which has gone inside the cells. And you can see the whole lot has gone completely red, which means that the cytoplasm, the whole cytoplasm is completely stained, so the cap is completely open, so you just release the chromophore inside these cells. Okay, and if you just merge together, you can do it. So the next thing is to test the cytotoxicity with camptothecene. So here we just put the drug inside. This is a result with the nanoparticles without camptothecene. And then this is camptothecene in green. You can see that we have around 35% of cell death. And if now you use the nanoparticles, we can get the same kind of results. What I must say is that here we are using 40 times less of camptothecene than here when we are using the pure camptothecene system. It's less. Not only you are using less, but you are releasing it directly inside the cells. Okay. Next thing we want to do is to just use two multifunctional system. Sorry, it doesn't. Multifunctional system where now we have 2 grafted systems. And to do this, we are going just to activate stimulate one of these functions, which will deliver either a proton or electron. And this can help in uncapping this system. So starting from this, we have a mixture of TOs, trisilane, and then propylsilane. This is our bridge system. We are going to mix all of them and do some nanoparticles, mesoporous nanoparticles. And in this case, we will have these 2 functions which can be clicked by the tube copper azido-alkyne system. So what we can do is just by using copper catalyst, click here an azido system to get 1 function, and then click here with an alkyne function to get the other function. Okay? So this is the idea. On this system here, for example, the acido, we are going to click something which can block the whole system. No, we are going to click something which can start which can be activated by light, for example. And then the second one is going to be clicked here. It's just the capping system here. And just by irradiating here, you will just deliver, for example, a proton, and this proton will just react inside and will just open the cap. Okay, this is the idea. You click here the photoacid, and you click here an amine with which we are going to afterwards put the cargo molecules, for example, vitamin B again, chromophore, and then we cap with cyclodextrin, which will form a hydrogen bonding between the hydroxyl group of cyclodextrin and this amine. And from here, we just irradiate, and from irradiation, this is the photoacid, you will just deliver a proton to protonate here, and after protonation, you just cleave the hydrogen bonding and you open the cap. Okay? So then from here, you just have directly, and as you can see, without laser, there's not much delivery of the chromophore, and as soon as you put laser on, you have a fluorescence that's just delivered. Okay, the next thing, the last thing I want to show you here is how we can transfer the energy from the walls to the cap. Starting from this, I just want to show you, the first thing is that with this diazobenzene, we can form by isomerization, just by irradiation, you can form this cis-trans isomerization system. Okay? And we are going to use this just to create some motion into our materials. So use this as a propeller, as you can see. So this was already done in 2008 by Jeff and who put some chromophore inside mesoporous silica, and into which he could graft the diazobenzene, and when he put elimination, he could just create the isomerization, and not only the isomerization opens the holes, but they are also creating some motion, so they are kicking out these molecules. The thing is that he could not do it much better because he was using only one photon system. What we decided to do with him is to use now a two-photon system. Why two-photon system? It's because compared to one photon, which is only surface irradiation, and which will attack most of the surface where you are radiating. If you use now two-photon system, it's only a focalized spectrum, and it will penetrate down to 1 to 2 centimeters into the body. Okay? And this one will just be on the surface. So this is quite interesting, and also it is, it is not harmful to the body because we are using near-infrared excitation system. Okay. The idea, of course, is to get again the nanoparticles inside the cells, and as soon as it gets inside the cancer cells, then we apply the two-photon system, and we will open the cap here. Okay? So here is our bridge cis-dioxane and another organocyanine which will create the motion. You have the diazobenzene here. So by co-condensing this in with surfactant, we can get this kind of mesoporous material which is here. And this mesoporous material will contain these bridging units here, which is a two-photon system, two-photon fluorophore, which will be in the walls, while this will be pendant groups inside the holes here. So the idea is to use this chromophore to absorb some energy, two-photon, and then to emit his energy, which can be transferred to this isobenzene, so that we can create the isomerization and then create the propellant system. Okay, so here it is. So we were lucky to have, but of course we thought about it, to have a good emission of the fluorophore, which is here, and a good absorption of the isobenzene, which is here. And luckily, there's an overlapping of these two emission and absorption spectra. And thanks to this, we can transfer the energy. Okay? So, and thanks to this, two photon system would just emit, and then this emission would be captured by the diazobenzene, and we will create a reaction. So to prove this, we prepared three kinds of nanoparticles, which I call materials azobenzene alone, materials fluorophore, and then the one we wanted, materials with azobenzene and fluorophore, azobenzene inside and fluorophore on the walls. Okay? So as you can see, all of these are nanoparticles and mesoporous nanoparticles, from spheres to nanorods. And I will just talk about these two MA and MAF nanoparticles. If you look at the MAF, you can see that the cells here, when stained here, are completely green. And unfortunately, you can't find it, but believe me, on the arrows we have the nanoparticles. You can find the nanoparticles which is inside when we put some, for example, when we put these, for example, breast cancer cells. Okay? And thanks to the fluorophore, you can reveal these by photoluminescence. Okay? So, and then if you merge this, you can see it also here. And the result is here, is that if you irradiate the cells, nothing happens. Okay? Then if you take the nanoparticles without fluorophore, MA, you irradiate and you don't irradiate, you get the same results. Nothing is happening. Whereas if you use the fluorophore with the azobenzene materials, then you get something completely different. When you irradiate, you kill the cells down to about 25%. So it works. Okay, I will just end my talk with two last work we've been doing. We've been doing these nanoparticles, but still people say that they are difficultly removable from the body. So what we need to do is to get them smaller again. So what we decided to do is to form some system, here, which is a bis PMO with a disulfide, which I call dis, and a ethylene with this silane, which I call E, and both called PMO E-dis. And if you prepare this, then you can have the sulfide here, which would just be bridging on the walls here. And just by using, this is known to be easily cleaved by methyl glutathione, and we just use mercaptoethanol to prove that we can do it. Okay? Right, this is the answer. Just by using TEM, we have the nanoparticles here. When you treat with mercaptoethanol, you can see that these nanoparticles are just getting smaller and smaller. Okay? And you can prove this also by DNAs. Next thing we did, I was talking about nanoparticles which are not mesoporous dense, which are dense, and we can use this sort of bridge system, and we can make three sort of materials. We can do first the bridge cis-dioxane, fluorescent, due to the two-photon system here, but we can then decorate with, for example, gold nanoparticles. And then we can, on the other side, we can first use the gold nanoparticles and cover it with the bridge cis-dioxane and get these three sort of things. We show you next that thanks to these gold nanoparticles, we have here some photoluminescence, and thanks to these gold nanoparticles, this photoluminescence is really enhanced, and this can be used. This is 10 pictures of these nanoparticles, and this can be used for imaging. Okay? So you can get, for example, here you can find the nanoparticles of these things here, and then you can get an enhanced fluorescence due to these gold nanoparticles, bridge cis-dioxane nanoparticles. And more interestingly, you can use them to kill cells. So this is just irradiation of the cells. And then if you put the nanoparticles of the bridge cis-dioxane here, you can see that you can kill down to 75%. And now if you take both separately, you can go down to 6 and nearly to 0%. So you're killing all the cells. Okay, I think I've finished my talk now. And I just want to summarize what I've been talking since Monday. So, bridge cis-dioxane, I showed you that we can prepare structured materials. From this, we can prepare self-structured materials. These are what I've on Monday. You can also prepare PMOs. I talk on Monday also and just give you some ideas about the nanoparticles. And I talk also about molecular recognition to show pH-sensitive system, and you can combine these to get some drug delivery system. And we've been working hard since this past, I would say, 5-6 years to get these results. I also showed you today that we can prepare some amorphous materials. For this, we have also prepared some pre-recently used for this drug delivery system. And for our amorphous system, we prepared some sensors, and I didn't have shown today. We prepared photoluminescent materials. I have talked about this one for the films, and we also prepared metal uptake and torch media catalysis, which I gave you one example. For the catalysis, we have done 4 reviews, and we've been working on several kind of metals: palladium, ruthenium, rhodium, and then gold. And we are doing now also organocatalysis and photocatalytic system. Okay. I just want to thank for funding this free institution, ANR, which is the National Research Agency, CNRS, my employer. And then I want to thank also USC and my students who have been working on this. These 2 people from India and from Czech Republic, they were more or less involved in the work also. They did the click chemistry for functionalization. I didn't talk about it today. Okay? And all of them in blue, in purple here have been doing structuring, and those people have been working on the particles. And Sophia and Julia have been working with catalytic and also photoluminescence. I want to thank John for funding from his university, because we are working together with Alban, who is just finishing now a PhD, working on the pH-sensitive system. I want to thank also Rosa Plexas from University of Autónoma de Barcelona, with whom I've been working mostly on the catalytic system. Luis Carlos on the photoluminescent materials, Jeffrey Zink and Fuyu Tamanoe from UCLA. We started working on these nanoparticles, and thanks to also the French people from Mireille Borsaldesh from Bordeaux. She had the apparatus of the 2-folded system. And we have also our biologist here, Magali, who evaluated all of our nanoparticles. And finally, I will thank also my team here with Jean-Olivier Durand, with whom we started to work on these nanoparticles. Carol worked on the molecular recognition, and Xavier was working on everything: catalysis, nanomedicine, and also photoluminescence. And I want to thank you, and sorry for being so long. And I hope I've been able to show you what we can do with this sort of activities. Thank you so much.
Many thanks. It's really excellent work. Вы видели, что там непростая химия, зонгель-химия, здесь сопряжена с органической химией, очень сложные синтезы, включая клик-chemistry, но результаты впечатляющие. То есть работа Мишеля на высоком уровне. Это видно из того, сотрудничество тоже. I told about your excellent work in Russian. Really, thank you very much indeed for your nice lecture for young scientists. Thank you.